Hello everyone, let's analyze. So today I'd like to talk about the complete orthonormal family of Fourier functions. So we've mentioned these Fourier functions and we've offered them as an orthonormal family for function spaces, in particular the L2 space which we built in the last lecture. Today I'd like to prove to you that they are complete and discuss when and how they converge. So we have two different ways of describing these Fourier functions. We have the functions e to the I n x divided by the square root of 2 pi for all integers n. That means n ranges from negative infinity to infinity, where n are integers. Or we have the union of the normalized constant function, that's 1 over square root of 2 pi, the normalized sine of nx function, and the normalized cosine of mx function. Here, n, the index for sine, and m, the index for cosine, are natural numbers, so they range from 1 to infinity. So these are known as the exponential and trigonometric Fourier functions, respectively. Now, note that in the definition, I said the interval from negative pi to pi. We could just as easily consider the interval from 0 to 2 pi, or rather any interval of length 2 pi. And of course, if we wanted to consider a different interval, we can, in a very straightforward way, rescale x for intervals of different lengths. So that's straightforward. So we're going to consider intervals of a period, right? Negative pi to pi. But the same ideas work elsewhere. Also note that the two families of Fourier functions are interchangeable. So I've offered two families of orthonormal functions, right? This exponential family of Fourier functions and this family of trigonometric Fourier functions. But they're interchangeable. And they're interchangeable in this sense. If f is an L2 function, then let f(e) n be the best approximation to f in the span of this family truncated at some capital N. Now, because n is an integer, we have to truncate both sides from negative capital N to n. And let ft be the best approximation in the span of these vectors truncated at a capital N. So we have the normalized constant, our sine of nx functions from n equals 1 to n, and our cosine of mx functions from m equals 1 to n. Now, we should point out that if I were to express f, if I could express f as a Fourier series, whether exponential or trigonometric, then by truncating it at some n, that gives us the best approximation from the span of that truncated family, right? And that's a direct consequence of the best mean approximation theorem, which we discussed previously. So here, if I find the best approximation in the truncated exponential family or the truncated trigonometric family, then they are the same, right? They're the same. And that's what I mean when I say that these two families of Fourier functions are interchangeable. You can use one or the other, you're going to get the same outcome. What that means is, when I give a result about one or the other, the result holds for both. And the first result, well, it's kind of the star of the show. I offer that these orthonormal families are complete, and now we will offer this as a theorem, that in fact, these orthonormal families of Fourier functions are complete in the L2 space on the interval from negative pi to pi. Again, we can replace that with 0 to 2 pi, or really any interval of length 2 pi. Now, the proof is rather long, a bit involved, but not too difficult. And it is given in your textbook in detail if you want to take a look at it. But what I will do is that I will give a sketch. And the sketch goes like this. The space of finite Fourier expansions, that is truncated Fourier expansions, are dense in the space of periodic. Now, when I say periodic, what I mean is f at the left endpoint equals f at the right endpoint. Right? It might be weird to discuss periodicity when I talk about functions defined in a single interval and not the real line. But what I mean is, if they're equal at the ends, then I can take a periodic extension and have periodicity because of that equality. So the space of finite Fourier expansions are dense in the space of periodic continuous functions. And I mean that they're dense with respect to the infinity norm. In other words, if I have any continuous function that are equal at the endpoints, then there's a truncated Fourier expansion that is arbitrarily close with respect to the infinity norm. That means it's arbitrarily close everywhere. Furthermore, the space of periodic continuous functions are dense in L2 with respect to the L2 norm. In other words, if I have some continuous function that is equal at the endpoints, then there's an L2 function arbitrarily close to it, where close is measured in the L2 norm. And if FL is a sequence of functions indexed by L and it converges to F in mean, and each of these FLs permits a Fourier series, then so does F. That means F can be expressed in terms of this orthonormal family, which would complete the proof. So that's the sketch. So let's expand upon this sketch of a proof. So let's describe the idea of that first bullet point as lemma 1. Let F map the closed interval from negative pi to pi to complex numbers. Suppose it's continuous and periodic in the sense that it's equal at the endpoints. Then for any epsilon, there is some natural number n, so that Sn, which is some function in the span of the truncated exponential Fourier family, such that f minus Sn is less than epsilon when measured in the infinity norm. In other words, f minus Sn at most for any value of x, at most is less than epsilon. Now, the proof actually follows directly from an application of the Stone-Weierstrass theorem. So recall that we actually proved a particular instance of the Weierstrass theorem for polynomials to demonstrate that polynomials are dense in the space of continuous functions. We can actually use the same machinery of the generalization of this theorem, which we offered as the Stone-Weierstrass theorem, to prove this lemma. Lemma 2, so this is the second bullet. Let f be an L2 function. Then for any epsilon greater than 0, there exists a continuous function, g, that agrees at the endpoints and is within epsilon of f when measured in the L2 norm. And let's give a proof of this lemma, well, a proof-ish. Again, the details are a bit involved, but let me just give the main ideas. And I don't want to spend a lot of time on the details because it's not really germane to the point of this lecture, which is that Fourier functions are a complete orthonormal basis. They do converge to functions in mean, and we also want to describe in what other ways do they converge. But the idea of the proof from lemma 2 is, since f is in L2, the absolute value of f squared is integrable, which means there exists some Riemann sum that's within half an epsilon of the integral of the absolute value of f squared. And the heights of those Riemann rectangles are equal to some value of f at some point Cj, where Cj are contained inside of my partitions. Well, the absolute value of f of Cj squared, I should say. Now, I could think of these heights of the Riemann rectangles as some piecewise constant function. Of course, a piecewise constant function is not continuous because it jumps from one constant to another constant. But what I could do is I could craft a piecewise linear function g so that g of x equals f of cj for all x in almost the entirety of the corresponding partition. But I could allow some gap for g to climb from the value of f of cj to f of cj plus 1 in a continuous, albeit steep, line across the partition interface. And if I make these gaps where the line goes from f of cj to f of cj plus 1, if I make these gaps small enough, then g of x will in fact satisfy lemma 2. Now let's consider lemma 3, which says that if f and fl are both L2, where L is some index of natural numbers, and for each L in the set of natural numbers, FL can be written in a Fourier expansion, then if FL converges to F as L goes to infinity, in mean, right, because of course when we say convergence in what metric, in the metric of the L2 norm, then in fact f of x can be expressed as a Fourier series. And this lemma follows from the more general lemma, which says that if V is an inner product space and phi n is a family of orthonormal vectors in V, and if f and fl are in V for each L in the set of natural numbers, and each FL can be expressed in the orthonormal family, then if FL converges to F as L converges to infinity in the norm induced by whatever inner product is endowed upon V, then in fact F can be represented in this orthonormal family as well. Now, the proof of this lemma will be in your homework. I can imagine you're probably looking forward to it. It'll be fun, I promise. Now, these lemmas come together to prove the mean completeness theorem in the following ways. Right? We have these lemmas. How do we put it all together? Well, remember, in order to say that the Fourier family of orthonormal functions is complete, we have to say that for any arbitrary f in L2, I can represent it as a Fourier series. So let's take an arbitrary function f in L2. Then there exists a sequence of continuous periodic functions fl such that f minus fl in the L2 norm is less than 1 over L. That follows from lemma 2. Therefore, fl converges to f in mean. And for each of these L's, there is a capital N such that fl minus Sn is less than epsilon over the square root of 2 pi. That follows from lemma 1. Where Sn is again this truncated Fourier series, right? Where for FL. Now FL minus Sn is equal to the integral of the difference squared. But that difference is everywhere bounded by epsilon over the square root of 2 pi. Or the square root, so when you square that, I get epsilon squared over 2 pi. When I integrate, I get epsilon squared. And since if I were to increase n, if I were to get some index n that's greater than or equal to big N, then this is smaller than this. How do I know it's smaller? Well, because if I increase where I truncate, right, then by taking larger and larger indices, I contain the previous space that I was considering. So the best mean approximation must get smaller and smaller and smaller, or at the very least stay the same. That follows directly from the best mean approximation theorem. In other words, if I find the best approximation for a space and then I enlarge the space, I should either get the same or a better approximation. Therefore, we have proven that FL minus Sn converges as n goes to infinity, which means FL can in fact be expressed as a Fourier series, and FL converges to F. Then from lemma 3, whose generalization you will prove in the homework, it follows that F, which is our arbitrary L2 function, can be expressed as a Fourier series. And that completes the sketch of the proof. Okay, I will let you go in and draw the finer details by following the proof in the textbook. And this demonstrates that both Fourier families of orthonormal functions are complete. Even though I only demonstrated for the exponential case, the equivalence of both the trigonometric and exponential Fourier families indicates that what is true for one is true for the other. Now, recall the expression f equals this Fourier series. We know that this is true for square integrable functions, right? It follows from the completeness of this orthonormal family. But just to be clear, and I know we know this, but if you'll allow me, I'm going to belabor the point. That does not mean that we have equality for each x in the interval. What it means is that we have equality everywhere except a set of measure 0. It also means that we have convergence of the series in mean. So this begs the question, when do we have pointwise convergence? When do we have uniform convergence? Let's take a look at some examples. Let's consider this function. F equals -1 for x less than 0, and f equals 1 for x greater than or equal to 0. So we can see that f is clearly square integrable. The square of f is 1 everywhere. The integral of 1 from -pi to pi is just 2 pi. So we know that in fact f does equal a Fourier series, in the sense that the difference between f and the partial Fourier series goes to 0 as n goes to infinity in the L2 norm. But what does this actually look like? So here we have our function in blue. F is -1 for negative values and 1 for x greater than or equal to 0. Let's take a look at the first Fourier function, that is, if we truncated n equals 1. Notice we get a sine wave. In fact, if we were to compute the Fourier expansion using the trigonometric Fourier family, we would only get sine terms. And why is that? Well, consider the oddness of our function. I'll let you contemplate. But as n increases, we of course converge to our function. But notice that because every term in our Fourier expansion is a sine function, our Fourier series is 0 at -pi, 0, and pi, but our function isn't. So we can't actually even hope to get pointwise convergence at those points. Notice that also any truncation of the Fourier series is continuous, but our function f is discontinuous. We couldn't possibly dream of uniform convergence because there's no way for continuous functions to converge uniformly to something discontinuous. That's impossible, right? And that follows from our previous discussion of function convergence. So we can't hope for uniform convergence. We know we have mean convergence, and it appears that we have pointwise convergence everywhere except the break in the middle and at the endpoints. So we don't get pointwise in our example at the discontinuities. So we need to be able to describe the nature of these discontinuities. So we say f is sectionally continuous on AB if there is a partition of AB, that is, a dividing of AB into intervals, right, whose union is equal to AB, for which f is continuous and bounded in the interior of each partition interval. Furthermore, we're going to say f of x naught negative is the limit as x approaches from the left of f, and f of x naught positive is the limit as x approaches x from the right. So in our previous example, f of 0 negative is negative 1 and f of 0 positive is 1. Now, of course, if f of x naught negative equals f of x naught positive, then we have that f is continuous at x naught. If, of course, those two limits agree and are equal to f of x naught. Now, this is going to allow us to quantify right and left derivatives. So the left derivative is the secant slope, where h is specifically, or h is our deviation from x naught, is to the left. And the right derivative is when the secant slope over a width of h is to the right of x naught. So in our previous example, both the left and right derivative were 0 because I had a flat slope to the left and a flat slope to the right. So the pointwise convergence theorem says if f is sectionally continuous, which our previous example was, and continuous at some x naught, or have a jump discontinuity at x naught, then if the left and right derivative both exist, now they don't have to equal each other, but if they both exist, then the Fourier series of f evaluated at x naught converges to the average of f at x naught positive and f at x naught negative. So if there's a jump discontinuity, for example, then the Fourier series converges exactly at the halfway point of the jump. And that's exactly what we saw. We had a jump to discontinuity that went from -1 to 1. The halfway point is 0. And in fact, we had pointwise convergence at 0. Now, if the halfway point of this is equal to f of x naught, then in fact we have exactly convergence at x naught. And of course, if a function is continuous and differentiable at a point, then you do get pointwise convergence there. So given this theorem and our previous function, let's analyze what happened. It follows from the pointwise theorem that for each x naught in the interior of the domain and not including 0, in other words, the open interval from -pi to 0 and from 0 to pi, we get pointwise convergence. However, for f of -pi, f of 0, and f of pi, we don't get pointwise convergence. In fact, we have that f of k pi is not equal to the Fourier series evaluated at that point, because the Fourier series at those points, -pi, 0, and pi, are exactly 0. Yet, we can still say, even though we don't have equality at every point, we can still say that f equals the Fourier series, and we can say that it equals the Fourier series in mean, But also we can say that it equals the Fourier series in the L2 equivalent sense, because the Fourier series and f differ, right, only on a set of measure 0, because it differs at 3 points. Now, is there a function that is equivalent to f for which we have pointwise convergence everywhere? Sure, we just take the pointwise convergence of the series. In other words, can we change the value of f at just a few values? And what do I mean by a few values? Well, either a finite number or a countably infinite number. Well, in fact, we only need 3 values to change. So the answer is yes. If we say f is -1 or 1, for the points that we do have pointwise convergence, in other words, in these 2 intervals, we get -1 and 1. And at -pi, 0, and pi, we let f be 0. So if we were to change f to this, now by the way, this f and this f are equal in the L2 sense, in the sense that they are equivalent because they differ on a set of measure 0. Let's take a look at what that looks like. So here, notice that our function has changed slightly, even though it is equivalent to what it was in the L2 sense. But it changes that now the value of our function is 0 at -pi, 0, and pi. Our Fourier series is exactly the same. Again, it's going to be a sine series because of the oddness of our function. Now, notice in this case, we get pointwise convergence everywhere. And, of course, we get convergence in the mean because this is still an L2 function. In fact, it's the same L2 function as before. So, we know that if there's a discontinuity, we can't possibly get uniform convergence because the truncated Fourier series are continuous. So it begs the question, when do we have uniform convergence? Is it enough for f to be continuous? Is that sufficient? Let's take a look at another example to shed some light on this. So let's consider this function. This function appears to be continuous. Will we get uniform convergence? Let's take a look. Notice again, for n equals 1, we just get a sine wave. In fact, again, our function is odd, and again, its Fourier expression will be a sine series. So here I stopped at n equals 5, and it appears to be converging to the function, except that because we're necessarily going to get a sine series, my function is actually going to be 0 at -pi and at pi. Right? My sine series, my Fourier series, which is a sine series. However, the function we're representing is not 0 at -pi to pi. So it doesn't appear, even at the early stages of convergence, that we will get uniform convergence. But why not? Our function is continuous. Well, in fact, our function only appears to be continuous in the sense that is relevant to us. There's actually a discontinuity hiding in plain sight. Now you might ask, what discontinuity could you possibly be talking about? This blue function is clearly continuous. But remember, we're only looking at the interval from -pi to pi, but there's nothing that prevents our Fourier function from being evaluated anywhere. And our Fourier function is periodic. It has a period of 2 pi. So we can expand. And if we look at a Fourier function expanded, it is continuous. It is continuous for the entire real line. But if we took a periodic expansion of f, notice that because f at the left and right endpoints don't equal to each other, then a periodic expansion reveals discontinuities at every odd multiple of pi. So in fact, our function cannot be periodically extended in a continuous fashion. Therefore, it is impossible for our Fourier function to converge uniformly to something that is discontinuous. It is impossible. We will converge pointwise for every x in the interior of my domain of negative pi to pi, but not at negative pi and not at pi, because I don't get a continuation, a continuous continuation of my function if I were to tile it in a periodic way. So in order for there to be any hope of uniform convergence, I would need not only that my function be continuous, but that it could be continuously extended periodically across the entire real line. And that would require that f of negative pi and f of pi are equal. And that brings us to the uniform convergence theorem. Let f be continuous on the interval negative pi to pi, and let f of negative pi and f of pi be equal. This allows us to extend f periodically to the entire real line and be continuous everywhere. And suppose the derivative of f is sectionally continuous with jump discontinuities. In other words, suppose that f, while continuous, has some corners. Then the Fourier series converges to f absolutely and uniformly. So let's take a look at the proof. We know from the pointwise convergence theorem that I can express f in a Fourier series. In fact, that follows from the completeness of the Fourier family. But from the pointwise convergence theorem, we know that we actually get convergence at each x pointwise. Now, notice how I wrote it in kind of a weird way. I wrote the zeroth term separately. And notice how I wrote e to the I 0x. That's just 1, but I wrote it in this way just to emphasize that this is the zeroth term that was removed. And for the sake of simplicity, I'm going to call this coefficient here an. Now, f prime from the pointwise convergence theorem can also be expressed as a Fourier series. Now, of course, because I have jump discontinuities, I may not get equality at those jump discontinuities, but in the L2 sense, I do have equality. Now, notice I don't have a constant term. Why don't I have a constant term? Why is the zeroth term of f prime necessarily 0? I will leave that enigma to your ponderings, but I bet you can figure it out. I'm going to call the coefficients of the derivative alpha n. Then integrating by parts and applying the periodicity condition yields that alpha n is, right, by definition, 1 over 2 pi times the inner product of f prime and e to the I n x. That equals in over 2 pi times the inner product of f and e to the I n x. In other words, I get in times an. In particular, the absolute value of an is the absolute value of alpha n divided by the absolute value of n. Remember, n could be an integer, so it doesn't necessarily have to be positive. Let's continue the proof. Let Sn be the truncated double-sided series adding up the absolute value of the coefficients an, where n is going to go, of course, from negative n to n because we're truncating. Well, remember, the absolute value of an is the absolute value of alpha n over n. And here we can use the Schwarz lone star. Now, if you're not from Texas, then you can just take lone star as a term of affection. But this inequality is in fact directly a result of the Cauchy-Schwarz inequality, because I can take this left hand as a dot product of the vector whose terms are the absolute value of alpha n with the vector whose terms are the absolute value of 1 over n, where again n ranges from the indices indicated. So Cauchy-Schwarz says that that's less than or equal to the norm, and since this is a dot product of vectors, it's just a Euclidean norm. It's less than or equal to the norm of each, which is exactly given by this. Now, this term actually does converge as n goes to infinity. Furthermore, because the series has only positive terms, this truncated series has to be less than the full series. And in fact, this converges and this converges. This is exactly the norm of f prime squared divided by 2 pi. And this, we know from Basel's problem, is pi squared over 6 times 2. Times 2 because notice it's a double-sided. Right, it's double-sided. So I'm going from 1 to infinity and negative 1 to infinity. But of course, for the negative values of n, I'm squaring it. So I'm getting basically the sum from 1 to infinity twice. So I get 2 pi squared over 6. But this indicates that Sn is a monotonically increasing sequence because I'm just adding positive terms, and it's bounded for all n. Therefore, it must converge. This, right, converges as capital N goes to infinity, which is to say that this series converges. And it follows that this series converges absolutely and uniformly by the Weierstrass M-test. And that proves our theorem, that the Fourier series for f converges to f both absolutely and uniformly. Now, let's take a look at an example where uniform convergence is guaranteed by the uniform convergence theorem. And let's see if we actually do get uniform convergence. So let's let f be the function here in black. Notice that it is continuous. F has the same value at the right hand and the left hand side. I've already put the Fourier series truncated at 1 up on the graph. And here, just for the sake of illustration, I actually picked a specific epsilon of 2 to the negative 4, or 1 over 2 to the 4th power. That means if I let n get big enough, my truncated Fourier series will be completely inside this blue dashed ribbon that surrounds my black function, which is continuous. Now notice it has corners, so it's not differentiable everywhere. Right? The derivative is sectionally continuous. And yet, this does satisfy the hypothesis of the uniform convergence theorem. So I should get that these continuous functions converge uniformly. In other words, my entire truncated Fourier series should be contained inside this blue dashed ribbon. And it only took me n equals 12 to get there. Well, what if we chose a smaller epsilon? So what if we had epsilon is 1 over 2 to the 8th power? Now our blue dashed ribbon around our function is so small as to be apparently right on top of it. Let's see if we get convergence. Now remember that my truncated Fourier series is continuous, but also infinitely differentiable. It has no corners, and yet it converges uniformly to this function. If we were to zoom in, we would see that it's completely contained in the dashed blue ribbon around our function. Let's zoom in just a little more. And there we see that we get uniform convergence. In fact, we get uniform convergence for any value of epsilon. So, of course, if we were to check all values of epsilon, it would take forever. That's an infinity joke, because it's true for every positive epsilon. But just for fun, let's take a look at 2 to the negative 10. So that's about 1 over 1,000. So that's fairly small. And remember that we have this jagged function, right? It's jagged. It has corners, but it is continuous. The values at the endpoints do agree. The derivative is sectionally continuous. The derivative has jump discontinuities at the corners. And yet my red truncated Fourier series, right, truncated a capital N, that is increasing before our eyes, converges uniformly to this jagged function, even though our Fourier series is infinitely differentiable. And in fact, at n equals 828, we nailed it. We're within an epsilon ribbon of our function everywhere. And let's zoom in just to visually confirm. Right, in fact, we are completely inside our blue ribbon everywhere. So now we know that if f is an L2 function, then its Fourier series does converge to it in mean. We can quantify when we have pointwise convergence, and we know that the only way we can have uniform convergence, right, the only way that it's possible is if we're continuous and agree at the endpoints. And if we're continuous and agree at the endpoints and have a derivative that's sectionally continuous, then we are in fact guaranteed of uniform convergence. Now, there are in fact other theorems, some less stringent, that will guarantee uniform convergence or pointwise convergence. There are several, in fact. We're not going to get into it, but some of them are described in your textbook. And I urge you to take a look at it. But these are the two most important and most relevant for many areas of applied mathematics and, well, analytical concerns as well. So we're going to stick to these. When do we have L2 convergence? When do we have pointwise convergence? And when do we have uniform convergence? That's it for today.